Okay, welcome everyone. Bienvenue à tout le monde. The second talk of the 2022 medal of the CAP. The winner of the CAP-TRIUMF Vogt Medal in Subatomic Physics is Asimina Arvanitaki. And Asimina is from the Perimeter Institute, and she is now going to give a short exposition to her work. Please, Asimina, share screen and go ahead.
Thank you, Manu. Okay, here we are. Let's play this. Okay, so thank you very much for this. So for this talk, I've chosen to present to you some part of my ongoing work that has to do with the cosmic neutrino background. And in particular, its distribution on the surface of the Earth. But before I do that, I would like to put this work at a much broader context. And as you will see, this has some overlap with what David talked about. So in particle physics, what we try to do is reduce nature to and describe it with the least amount of ingredients and the least amount of equations. And this has been an effort that has been ongoing for decades. And in fact, depending on how you count, you can say it started with Newton. But what we've managed to establish so far is the standard model with the leptons, the quarks, the three families, and its gauge bosons that mediate interactions between them, and the Higgs particle that was discovered in 2012 at CERN. And this is a very successful theory, okay? So it has 20 particles and 20 parameters, and we know we can apply it from the biggest scales. We can apply the laws that the standard model includes to the universe itself, to galaxies. It describes the physics on Earth. And we've actually managed to test it. The standard model is a very successful theory. We've managed to test it to very short distances. So we know it works in nuclei and subatomic, subnuclear distances, in fact. We know one of the great successes of the standard model is that we've managed that quantifies how successful of a theory is. We've measured some properties of the electron, for example, and we found that experiment and theory agree to 13 decimals. So this is, you have a decimal point, there is 12 zeros, and then there is the first significant 12 to 13 decimals, the first significant digits right there, which is a great achievement to be able to do. Now, the way we've mostly gained this insight about the fundamental laws of nature has been through the Collider program. Every time, so over the past decades, we started with colliders fitting on the palm of our hands. So we accelerate particles, either on a line, on a circle, and we collide them. And from the collision products, we can understand, we have discovered new particles, we have discovered these interactions. And the culmination of this is, in fact, the Large Hadron Collider, which, as I said, and as David said, discovered the Higgs in 2012. Now, and this is what is known as the high energy frontier. So every time we go higher and higher energy, we discover something new. But this is only part of the full story, okay? So if one looks at the totality of scales that we know of in our universe, from the size of the universe itself, the Hubble scale, to the Planck scale, there is 80 orders of magnitude roughly that remains unexplored. We know, for example, there is all sorts of physics that cannot be discovered with colliders. So we need a direction that's complementary to it. And this is where my work comes in. So it goes usually by the name of the precision frontier, where you try to devise experiments that try to look for the tiny, tiny deviations from the standard model. At the same time, though, it takes into account that over the past decades, there are other fields of physics that have made tremendous progress in how well they can measure tiny effects. For example, the current standard of time is set by atomic clocks. So atomic clocks, for example, their ticking rate is extremely, they are precise to 1 part in almost 10 to roughly 10 to the 18, 10 to the 19. What does it mean? Well, by some measure, a wristwatch loses 1 second every year. Okay, if we were measuring the same time with an atomic clock, if we translate the same quantity for an atomic clock, it would mean that the atomic clock loses 1 second every 100 billion years, which is an extremely amazing achievement. So if there's any new physics like dark matter or any new forces that would affect the behavior of these clocks, you can try to look for it. Now, there is all sorts of other experiments that one can imagine doing based on these developing technologies. Now, for the remainder of my talk, I would like to focus on, as I said, on something that I'm doing now and fits well with this program, and it's work done in the cosmic neutrino background. And in order to tell you, maybe some of you are not very familiar with it, so we'll start with a brief history of the universe. So we believe that the universe started from a big bang, it expanded, and as it expanded, things inside it started cooling. At some point, nuclei, the protons and neutrons formed, then nuclei formed, and then at some point, atoms, meaning protons and electrons, bonded together into hydrogen, they formed, and eventually today, and then after that, galaxies formed, and we find ourselves today with a universe that's roughly 10 billion years old. A very important time in this history is the time of the cosmic microwave background, okay? And basically, this is the time where atoms form. So when protons and electrons bind together into atoms, then light from the Big Bang could travel large distances. So the universe became transparent to light. So this is what we know as the light from the Big Bang, essentially. So this happened when the universe was just 400,000 years old. And this is a picture of the cosmic microwave background. It's of course microwave because that's the frequency of these photons from the Big Bang appear today. And this is a picture from the Planck satellite. So as you can see, we've taken a picture, a snapshot of the universe when it was just 400 years old with extreme precision. And in fact, the discovery of the cosmic microwave background, which goes back in the 50s and 60s, has allowed us today to turn cosmology into precision science, because we know that what the universe is made out of down to 1% precision, which is amazing. It's an amazing fact. Now, let's go back to this picture. As I told you, this is the CMPs right there at around 400,000 years. Now, if you go even further, there is another type of background of Big Bang relic, which goes by the name of the Cosmic Neutrino Background. And this was formed at the time of, much earlier, at the time of when the universe was around 1 second. First of all, and this has to do closely to the fact that we are talking about neutrinos and not photons. And the reason is that these neutrinos are, for those, I don't know, the audience may be born broad, so I apologize to the particle physicists for this slide. So neutrinos are particles very similar to electrons, but they have no charge. So they interact with us extremely, extremely weakly. And turns out they are closely related to radioactive processes. They are produced routinely in radioactive decays. So they were first proposed by Pauli and better understood by Fermi back in the 30s, when they were observed in decays of radioactive elements. And since then, we've been trying to study them for decades. The latest of which, the latest the latest advancement in this field happened in recognition of the advancement that has been happening in this field of neutrino research came in 2015 with a Nobel Prize that Kajita and Art McDonald received for their experiments that studied the fundamental properties of these neutrinos. Okay. So now, what is the cosmic neutrino background? So, as I told you, these neutrinos interact extremely weakly. So the universe became transparent to them at a much higher temperature. So that means much earlier, at the time much earlier than when the universe became transparent to photons. So the universe at the time was just one fraction of a second old. And since then, as I said, they propagate freely. Today, as the universe has expanded, they have diluted down to roughly 100 particles per centimeter cubed. So they are very dilute, and they are extremely cold. Their temperature is only slightly below that of the temperature of the cosmic microwave background. And there are roughly equal numbers between neutrinos and antineutrinos. Okay. So if detected, the cosmic neutrino background is important because if detected, it would give us a snapshot of the universe at a time where it was much younger than what we've taken a snapshot of it from the CMB. So we would know, we have a picture of the universe when it was just a baby, 1 second old baby, or even smaller. The other thing is that neutrinos, despite the valiant efforts of many people and the continuing efforts of many people, it's largely an unknown part of the standard model. We haven't measured, we know they have masses, and that's a component beyond the standard model. We haven't measured their properties very precisely. So a combination of these things makes them a very interesting probe of not only standard model processes, but also beyond the standard model physics. So, and this is where my work comes in. So for the past year, I've been thinking about the properties of the cosmic neutrino background and new ways to detect it. And in this talk, I will give you it's only part of the research of the work that I have been doing. And I will tell you something about what we realized about the Earth. The Earth can significantly modify the local distribution of this cosmic neutrino background. So first of all, there is a very, besides the many quality, there is, as I keep saying, well, we haven't discovered, we know it's there, the cosmic neutrino background is there, but we have yet to discover it in a laboratory setting. In fact, we know it's there. One of the cosmic microwave background tells us it's there indirectly through the force of gravity. But we haven't seen it in a lab. And the reason is basically these neutrinos interact extremely weakly with matter. So traditionally in particle physics, the main thing we try to do things is through scattering. So particles we either collide, scatter particles with each other, or we do indirect searches for dark matter. We have a dark matter particle coming in, kicks something in a detector, releases some energy, and this is how we see it. Now, if you were to calculate the interaction cross-section for the cosmic neutrino background, one would find that that's extremely small. I mean, I have an estimate here of that, what the cosmic neutrino background interacts with matter, and this is 10 minus 64 centimeters squared. Strong interactions are 40 orders of magnitude larger cross-section. Just to give you an idea, 10 minus 64 centimeters squared might as well be 0. This is a mean-free path larger than the size of the universe. It's in matter, so it's ridiculously small. Now, this has been, of course, an ongoing issue. People have known about the possibility of having this cosmic neutrino background for a while. And in 1962, Weinberg wrote a paper where he managed to actually enhance by a little bit, by quite a bit, this interaction cross-section. And he said, well, in same way the neutrinos are observed in radioactive decays, you can imagine doing some sort of inverse thing where you actually absorb neutrinos in radioactive nuclei. And what he calculated is what you see here is a tritium atom, which is unstable, can absorb a cosmic neutrino, a relic neutrino from the Big Bang, and convert itself into helium and emit an electron. So this is and this cross section is much larger than what I presented before. And it has been there's been a proposal, I think now it's more than 10, 15 years old, to actually look for this process. Now, this proposal, which goes by the name of Ptolemy, has several challenges. One of them is that, well, tritium is radioactive, so it decays the normal way without absorbing a relic neutrino. And if you compare the absorption rate of a relic neutrino to the ordinary decay rate, you find that there is roughly a hierarchy of 27 orders of magnitude between the rates. So the backgrounds for this type of experiment are ginormous. Now, the cosmic neutrino background, though, because it's very cold, it has also another very important way it can interact with us. And that is by refraction. And this refraction is different from scattering. So because scattering is proportional to the coupling squared, while refraction is only proportional to the coupling of the neutrinos to us. And the refraction is something that we don't normally associate with elementary particles. Even though people, for example, people like Fermi knew he was doing a refraction of neutrinos with in his radioactive when he was playing with radioactive material. So basically, it's the same thing as light. So you have, if you take, for example, for light, you take a prism, as you see in this picture, you take a beam of light, and the beam of light bends, and it bends depending on the color of light. Okay, similar with neutrinos, as they go through matter, they will bend. So there is an effective index of refraction. So for the more formal people in the audience, this is related to the forward scattering amplitude of the neutrinos. That's why it's 1 power of G Fermi there. And for light, the bending of light, you can see it even in the picture, is quite substantial. You change the trajectory of a beam by order 1. But for neutrinos, this change and this bending is really tiny. And in fact, you find the difference of the index of refraction from 1 is 1 part at best, something between 1 part in 10 to the 9 and 1 part in 10 to the 8 for the cosmic neutrino background. Now, it's still a small effect, but given that is proportional to G Fermi, people thought, well, we have something that it's not giving us a lot of suppression. So this has been on for a while, of course, and there were several ideas that were put down on paper back in the 70s and 80s that said, so you have the prism, I have a beam of neutrinos going through, and as it bends, let's say it bends this way, it should give a kick in the opposite direction to the prism. So I can try to look for the recoil force. Now, people quickly realized that because neutrinos are coming from all directions, and there is no gradient in the density, they said there is no force, and this created a no-go, which in fact put a lot of dampened down a lot of the efforts. In fact, killed this G Fermi, this effort to find effects proportional to G Fermi. The only thing that survived is the Stodorsky, what is known as the Stodorsky effect. So if you have a spin inside the neutrino background, there is a difference in the energy between spin pointing up and down, which is more than 20 orders of magnitude smaller than what we have measured so far in the lab. So what I will talk about, in fact, is something that has been missed. I will talk about actually an effect that not only is proportional to G Fermi, in fact, is proportional to the root of G Fermi, and enhances the neutrino and antineutrino asymmetry on the surface of the Earth much more than you have in vacuum. At the same time, it also creates large inhomogeneities in its distribution. So the index of refraction one can understand perhaps very simply from energy conservation. So basically, the index of refraction measures how much the energy of a particle moves as it goes through, going from outside, from vacuum to inside material. Okay, so it's proportional for neutrinos to the interaction energy between neutrinos and matter, which is proportional to G Fermi, the density of atoms inside the material, and a proportionality constant that has to do with a weak charge. Okay, so it's proportional roughly to the atomic number of order the atomic number of the atoms in the material. Now, if you work out the numbers, you see that this interaction is repulsive for electron neutrinos and mu and tau antineutrinos. So it flips sign depending on the flavor of the neutrino, and it's attractive for electron antineutrinos and attractive for mu and tau neutrinos. So for the rest of the talk, I'll just stick with electrons, neutrinos, and I'll just refer to in general neutrinos and antineutrinos to describe this effect. So this interaction energy, I mean, still it's proportional to 1 part of G Fermi, still very small. It's anywhere between 10 to the minus 15 and 10 to the minus 13 eV compared to an energy of 10 to the minus 6 eV, kinetic energy of 10 minus 6 eV of the sigma B. And the main reason that the Earth can have a significant effect is the following. So because antineutrinos are attracted towards the Earth, they have an attractive potential, as they go through the Earth, they accelerate, they move faster. So if you take rays of antineutrinos, you see that they bend away from the surface. Now neutrinos, because they are repelled, they have to slow down. So eventually, these rays bend towards the surface, and eventually neutrinos will be coming in at such a small angle that they will be reflected from the surface of the Earth. So this total reflection is what creates the asymmetry of these neutrinos. So in fact, and this is the very pictorial picture, in fact, mathematically, what you have to do is simple quantum mechanics problems where neutrino waves interact with a square well potential. Okay, so typically the momentum, most of these waves know nothing about this potential because this height of this potential is very small, but there is a small fraction of these neutrinos that don't have enough energy to penetrate the surface of the Earth. And because of wave effects, there is a little evanescent wave, if you remember from optics, that there is a non-classical penetration of neutrinos around the surface. So this is it's exactly analogous to reflection of light on in the interface between two surfaces. As I said, the condition that neutrinos cannot penetrate is that they are momentum perpendicular to the surface. Their kinetic energy perpendicular to the surface is less than the interaction, than the height of the potential. So this is the equation right here. And if you convert this into natural units, as we do, you find that this critical momentum for reflection is the square root of 2, the neutrino mass, and the square root of the interaction potential, and it's roughly a scale of 3 meters. Okay, so this is much smaller than any cosmological scale that one can imagine. So basically, because of the slowdown, as I said, you get an excess of neutrinos close to the surface interface between the air and the inside of the Earth. Now, the amount of neutrinos that do this has to do with neutrinos that come in through the critical angle, which is the ratio between the overall momentum of neutrino and the critical momentum for reflection. And this, if you plug in the numbers, this is fraction 10 to the minus 4 fraction of neutrinos. Now, this is still a small number, but it's 5 orders of magnitude larger than the naive expectation in the standard model, which is 10 to the minus 9. Okay, so this means that the Earth, by just being there, changes significantly the distribution of neutrinos. And this is a plot that you see. This is the in units of the neutrino density, the asymmetry as a function of the distance from the surface of the Earth. You see the inside of the Earth and the outside for different neutrino masses, and kind of looks like this. Okay, so basically what you expect to see is that if you take an intersection of the Earth, you will depict a neutrino excess, a little fuzz at a distance of around 3 meters. So what I was telling you before, that the no-goes that said you cannot have any force now on a prism, it's no longer true. If a prism sits in that region, we'll experience a small force due to the neutrino background. Now, it's still a very small force, and what we're working right now is actually ways to make it bigger. But as I said, the mere presence of the Earth changes significantly due to these refractive effects, the local distribution of the cosmic neutrino background. So, and the reason that we are excited is because we think now we may have a chance to envisage a new type of telescope that will detect the cosmic neutrino background and give us a snapshot of the universe where it was just 1 second old. So just like when we saw the CMB, we discovered so many things. It's not, who knows what we will discover now. So with this, thank you very much. And I'm sorry I went a bit over time.
Okay, thank you. Thank you very much, Asimina. I open the floor for questions, but
yeah, I cannot read the questions for some reason. So do you mind reading?
Have to be asked in the chat.
yeah, I cannot read this for some reason. I'm having trouble seeing my. Yeah, okay.
If there are any, I will read them out. That's not a problem. But so far there aren't any. Okay, so I will ask some questions that I have come up with.
Okay.
So question, well, the most recent thought I had was, would the Earth's gravitational field cause the vertical component of these neutrinos to behave quantum mechanically in a gravitational background? Just like
so the effect of gravity is not, I mean, this is a quantum effect. It's because the neutrinos are waves, what I just described. So it's a pure quantum effect. So it's not, neutrinos actually, the great thing about neutrinos is that they are the things that are intrinsic quantum mechanically because they interact so weakly. Neutrino oscillations, for example, is a manifestation of quantum mechanics in all its glory. So you don't just need the gravitational background to do this. Now, the gravitational background, because it's such so long range, doesn't have the same effects that the weak interaction is still stronger than gravity here. So they change. Well, that's not really true. Basically, it's the interface. The fact that you have the interface between the vacuum, let's say, or the atmosphere and the inside of the Earth is what causes this effect. It's a short range. It also helps that the wavelength of the cosmic neutrino background is much larger than the interatomic distance. So you see it as a continuum soup. Okay.
So there is a question.
So I see. What do you envision this neutrino telescope to look like? Actually, in 2 weeks, I cannot, unfortunately, I'm not allowed to talk about it, but in 2 weeks, we'll have a paper out and you'll see. So unfortunately, I'm not allowed to talk about it. I wish I was. Like, if this was in a 1-2 weeks time, I would have been able to tell you, to show you a picture of it, but I'm not allowed to talk about it. But hopefully look out for our paper in the next couple of weeks. It should be out, and you'll get it's actually much simpler than people think. That's the great thing about it. So what does the asymmetry you calculate on neutrinos being Dirac? Yes. And how does the prediction change if they are Majorana? Excellent question, Tony. Excellent question. So this is something that we are thinking more carefully now, for the context, also for what we are writing. And we don't think it will change much. I mean, again, perhaps we can revisit it, and it should be something in the new paper about this. The reason is that weak interactions are parity violating. So you can think of the propagation of particles inside of either Majorana or Dirac neutrinos as similar to birefringence of light. So there is going to be a similar effect there's going to be the same effect for Majoranas as well. There may be a factor of 2 difference between the size of the asymmetry, but this is, I mean, we are still thinking about because the physics is a bit subtle. But that's what we think now. I hope that answers your question.
Okay, I think we should move on to the reading of the citations. So I will tell Asimina, congratulations, you have won the 2022 CAP-TRIUMF Vogt Medal for contributions to subatomic physics. And the citation reads, in recognition of your innovative contributions to a number of areas of fundamental physics, and in particular for identifying experiments that could test the underlying physics. So congratulations, and would everybody please show their appreciation by either putting up the clap signal or thumbs up, raise clap signal. Okay. Congratulations.
Thank you very much.
And,
thank you very, very much.
Yeah,
so for those of you who don't know me, I'm originally Greek. I grew up in Greece. And in Greece, the word for work originates from the same work as slavery. And I think I'm not the only one to say that for us, what we do, our work is not by any means slavery. This is a labor of love. We do this because we love to do it. And it's part of who we are, and we're always very excited to find something new and to work on physics. This is what we do. So to be recognized for something that you love, for the work of love that you do, is the utmost. I mean, it's the utmost honor to be recognized from your peers. So I would like to thank the CAP Association and the TRIUMF for this immense honor. I cannot imagine a greater gift to a physicist than the recognition of their peers. So thank you so much for this. I would also like to thank the Perimeter Institute for its continued support. I've been here for the last 8 years, and I'm grateful to have their support. I'm also, the work that you see is, again, the result of collaborative efforts. So I haven't been doing this by myself. So I'm over the years, I've been blessed to have extremely talented, both younger and more senior collaborators. At the same time, my research has been sponsored by the Gordon and Betty Moore Foundation and the Stavros Niarchos Foundation in Greece. So I wouldn't be able to do this without their support. And finally, I would like to thank the Canadian government because it looks like they understand the importance of fundamental research. And it's great to see their continued support for this, and I hope they continue to do it for the foreseeable future. So thank you all very much.
Okay, thank you very much, Mina, and congratulations on behalf of CAP. There was one question that came in afterwards by Sriram. It said, would you be able to discover massive neutrinos in your finding, and would there be
good? That's a very good question. That's a very good question. So in principle, yes. So because these and it will become more clear, this is something that we're thinking about. So if you were able to measure, for example, somehow the index of refraction, different neutrinos of different masses and different compositions interact differently. So you would be able to measure, if you were to detect the neutrino background, to measure specifically in the mass eigenbases now, the properties of these neutrinos. So you'll be able to tell more about their masses, we're thinking whether or not you'll be able to tell if they're Dirac-Majorana. And you'll also be able to tell if there's sterling neutrinos at play. So if discovered, the cosmic neutrino background contains tons of information about these particles. So yes, you'll be able to do this.
Okay, thank you very much. And are there more questions, people? We have 5 more minutes before the next talk by Charles Gale.
Yeah, so doula, the word doula that you guys use here for it's actually the word for slave in Greek. It's not a great word. I actually don't like it that much.
What is agathos?
Agathos means kind and I mean it depends. Agathos means good-hearted.
Ah, okay.
Thank you. Yeah, if you have any more questions, hopefully, I wish this was in a couple of weeks' time. I could have told you much more, but it's okay. The Earth is pretty cool because it's just there, and it changes the properties of these particles by quite some amount.
So thank you again, Asimina, for what a wonderful talk. I'm going to pause the recording now.